hear this during his talk, that his energy and his enthusiasm for science is just infectious. And it really comes through in his talks, and so should be a lot of fun stuff today.
Thank you. Thanks so much, and it's been just absolutely such a joy to be here the past 2 days. It's so, like, I've had a day of meetings that's been all booked up, which is very different than my sort of normal state of sitting quietly by my computer. But that's been just an absolute joy. And every half hour, there's been a new amazing sort of set of objects to think about and phenomena, and that's really fun. So I want to tell you a story about two particular systems, but they both relate to this idea of stars evolving and that evolutionary history being kind of intercepted by companion objects. And so, being kind of silly, I called this big stars and their little friends. And you can think about it if you want, sort of more in the vein of like, I was coming to California, there's people like Justin Bieber and all these little friends who follow him around, but if we stick more to the astrophysics, this is binary and multiple star systems. So stellar evolution, left to its own devices, converts hydrogen to helium, heavier elements, and when stars develop segregated structures, they actually expand a lot in size. And what that means is that when you have systems with multiple objects, then they can start out separate and evolve into sort of direct interaction. So first I want to tell you the story about an evolving star with a second star, kind of in the way of that evolutionary history. One thing we know about binary star systems is that they have very broad distributions of eccentricity. And so for every circular binary system, there are a number of eccentric binary systems. And one question we might ask is, as a system is evolving basically towards contact in the sense that mass exchange might start between them, it experiences stronger and stronger tides. And we might wonder, do tides act to both circularize the orbits of those systems and synchronize them so that they're tidally locked each orbit? And whether or not that happens is a competition between timescales. One of those is kind of the radius growth timescale of the star. So you can imagine that tides are getting stronger because the star is getting puffier and puffier. And the other timescale is the time that tidal dissipation is acting on. So how fast are tides getting stronger? How fast is the radius of the star growing versus how fast is dissipation changing the orbit? If dissipation is the faster process, then the orbit will become circular, synchronous. If dissipation is slow, then you can end up with the situation where tides get stronger and stronger while the binary orbit is still eccentric. And that leads us to some really kind of amazing objects. And one example of those are these systems called the heartbeat stars. They get their name because these light curves sort of look like an EKG diagram with a pulse. What we're seeing in the pulse is every periapse passage in this eccentric binary orbit, the stars are stretched out and distorted, and they show us a bigger surface area. And then as they fly apart, in many cases, you see these little wiggles in the light curve. And the little wiggles are the fact that the stars are left kind of ringing, oscillating in modes that are sort of characteristic oscillation modes of their structure. What's also kind of amazing is the modes that tend to be excited are often harmonics of the orbital frequency, and so they're really driving these through resonances and all sorts of beautiful phenomena. So you might notice the y-axis on this. This is parts per million, so these are on the order of a part per thousand, maybe 1% at most. The sources that were first discovered were from Kepler. So these are solar mass-ish stars. But more recently, those sorts of searches have expanded, and we've been starting to find more and more extreme heartbeat stars. So here's one example that has a 20% photometric amplitude. There's spectra that constrain its orbit, and It has an eccentricity of something like 0.6. And it's probably something like a 35 and a 10 to 15 solar mass companion. So we're seeing the tides on the 35 solar mass star. And that amplitude itself is really kind of interesting because it tells you something about the magnitude of the tidal distortion of the object. So if the amplitude is, photometric amplitude is 1 part in 1,000, on sort of 0th order, the geometrical distortion of the star, every close passage is, 1 part in 1,000. But if the photometric amplitude is 0.2, then all of a sudden we think that the star must have like a fractional distortion of something like 20%. So this is really something dramatic happening to this star every periapse passage. These black dots are our TESS photometry between subsequent passages, and we're zooming in right around the peak of that sort of pulsed light curve. And what I want to show you is that orbit to orbit, it's not exactly the same. It's like kind of the same, but not exactly the same. And also, as you fall off, you go from this like extreme distortion of the star to the two stars start to fly away and the tidal force disappears and the star is kind of left ringing, and you start to see those ringing features there. This particular source is also kind of amazing in that it has broad Balmer emission. So this is an emission line star. Those emission lines disappear at periapse passage and you just see absorption. And then they reappear again in phase. The violet to red ratio changes during the orbital cycle. So there's a lot of beautiful sort of features to this object that are different from what we see in those lower amplitude, lower mass heartbeat stars. So a lot of my work is in gas dynamics simulations, and I just asked the really general question of what happens at large tidal amplitudes. And so here we're looking at a slice through a gas dynamics simulation where we're simulating a three-dimensional stellar envelope, and it's going to be subjected to a tide from that little object, which is going to go flying by in an elliptical orbit just once, and it will raise a tide on the star, and we just sort of see what happens. So this is a slice through the orbital plane of density, specific entropy, and velocity on kind of the surface. And the reason why it's that weird shape is it's like a map projection. Okay, so you got a tidal distortion, and we'll watch it again. But what happens is it actually can't quite stay in phase with itself, and it ends up crashing and causing this big mess instead. So you start out with a smooth wave, and you end up with a big mess, and you can see that really reflected in the velocity features on the upper panel, where they started out kind of really smooth. Here, they develop these cusps, and then from those cusps, you decay into smaller and smaller features. And that's basically the action of turbulence, taking you from very ordered wave-like motion into sort of disordered motion. And I think what we're seeing in this case is really the same as any other wave-breaking phenomena in physics. So ocean waves break because as they're traveling towards the shore, as you get into shallow water, the crest travels faster than the trough. And so the top of the wave gets ahead of itself and it falls over, and then you go from the sort of ordered motion of the wave to the big mess of that foamy part. And that's sort of a technical ocean sciences term, I'm certain. In this case, what we see is a little bit different. So the wave actually raises the tide, and if you think about what we see happen is actually the tide, instead of the crest traveling faster than the trough, the crest travels slower and it kind of collapses on itself backwards. So if you watch the initial portion of it, the morphology of the wave breaking is a tiny bit different, but sort of the transfer of a smooth wave into shocks and then turbulence is kind of similar. So this is a very idealized scenario, but I spent a bunch of time actually trying to reproduce what we're seeing in this particular extreme heartbeat star. And so this is a simulation of that. We're looking at, again, log of density in a slice through the orbital midplane. This is the 35 solar mass star. That's the companion star. Every passage it goes by, and it disturbs the bigger, more extended star so much that it raises this strong tide. There's actually a little plume of material from the atmosphere that gets transferred, and it sets the more extended star oscillating. And if we zoom in, maybe watch through this periapse passage and then we'll zoom in, what we see is that those waves that are raised actually break. So here's the photospheric flux, and this is sort of the three-dimensional version of that same plot. But you might notice that every time the sort of surface is oblate but pretty smooth right now, and when the object comes around again, it stirs up a big mess. And so what we think is happening is basically that the amplitude of the tide is so large that it doesn't stay in phase. It loses phase coherence as through that passage, and it breaks, and it shock heats the surface, and it makes it turbulent. And that really directly affects what we see. So the first question in this is, like, can we reproduce those observables? Like, for example, the 20% photometric amplitude. And it seems like we can. So if I measure the fluxes from that surface, I can reproduce things like the light curve and understanding where those, and that tells us that the magnitude of the distortion each periapse passage is about right. And the lower panel is the radial velocity curve. Here I'm kind of zooming in on the periapse passage itself. So has this kind of, at least to me, a priori weird shape. So there's a dip and then a brightening, and that all has to do with our perspective on this system. So if we looked at it from a different angle, we would see a totally different morphology. But what happens is at periapse in line A there, we happen to be aligned, so these lower panels are from the observer's perspective, essentially. So we happen to be aligned so that we're looking at the kind of pointy cusp of the tidally distorted star, and that's pointing towards us as the observer. And that's gravity darkened because it's sort of further from the center of the star. And so we actually see this sort of darkened patch transit across our line of sight. And that causes the minimum. And then, like a kind of like rotating potato, when you see it side on, we see the biggest surface area, and actually this portion has the highest specific brightness, and that gives us the peak. So it's both a changing surface area, but also a changing surface brightness with this, in this oscillating star. Okay, so now we're taking the same slice through the orbital midplane, but we're flying along with that primary star in its orbit so that you can see that interaction a little bit better. And one thing I want to draw your attention to here is that the companion star comes along and stirs things up once per orbit, but all of these waves and interactions keep propagating around the star. And in particular, you can see here, look at all these kind of spiral shock features that are being launched off of here. So this crashing wave propagating around the star is generating this shock-heated, rotating atmosphere. And I think of this as being completely analogous to kind of the foamy surface of that breaking ocean wave, where turbulence has dissipated that ordered energy into disordered motion and heat. Okay, I keep saying this wave breaks, but it's kind of hard to see it in action going that fast. And so let's zoom in right here on where I would argue that's what's happening. So the companion star is passing by. This first panel is right near periapse. This is a third of a day later, 1.5 days later. And we're going to zoom in where those little boxes are in the middle. The upper panel is the divergence of the velocity. So red regions are where fluid is converging really strongly. When fluid converges a lot, it shocks on itself. So it doesn't like to pass through itself because it's fluid, and it shocks. And then this is a tracer of the specific entropy. So you'll see redder, you'll go from like bluer to redder colors where shocks are raising the entropy. And what you can see is this shock feature sort of develops and moves sort of through 6 o'clock in the lower panel, where the wave is kind of trying to propagate around the star, but buckling on itself and starting to fold back. And so you see this in this little cusp here, becoming the stronger feature here. And that's kind of the action of that breaking wave in this scenario. I mentioned that there's this shock-heated atmosphere, and that corresponds to those emission line features we see in a really kind of interesting way that depends on orbital phase. But in particular, every periapse passage, if the star is being tidally affected, the puffy atmosphere around it feels an even stronger tide, and it actually gets stripped off and thrown out of the system, and then it reassembles because there's a new breaking wave. So I think we're seeing a new kind of a rejuvenated atmosphere each time. And here's a sort of phase series of those amazing Balmer lines. This is the H beta line from Jaisingh et al. And what we've tried to do is sort of match the changing violet to red ratios as a function of time. And that's, I think, challenging without a really detailed model, but the disappearance of the line here has to do with kind of our perspective on the system and the fact that as it's being stripped, all the material is flowing towards you. And so it has a narrower velocity dispersion. And so rather than seeing the broad line, you see most of it hidden behind the absorption component. Okay, so I told you that this class of stars are called heartbeat stars. I started calling this a heartbreak star because it's a heartbeat star, but there's wave breaking, and so maybe it's a heartbreak star. I find it maybe not heartbreaking, but kind of amazing. But the sort of basic features are that every periapse passage, there's this extreme tidal distortion. In the frame of the stellar material, that tide is time varying because the orbit is elliptical and because it isn't rotating in synchronization, and basically the tide can't keep up. It raises in this distortion, but then it falls back down on itself. It shock heats as it does. The condition for that to happen is basically that the oscillation speed is faster than the sound speed at the surface. So if that oscillation becomes supersonic at any point, it shocks. And so we see this wave breaking, and then as it flies away, its free oscillation continues. That's the same as all the heartbeat stars that we've observed, but it has this extra feature of the emission lines from the shock-heated atmosphere. So I think this emission line feature is maybe kind of a key tracer if we start to follow these up and look for a class of objects among these systems. There are a couple amazing features of this particular story that relate to the action of the dissipation associated with that wave breaking. And one is that this star rotates almost at breakup. And so I showed you it being really oblate. It's so oblate because it's rotating at least 99% the breakup angular frequency within the uncertainties. And so its equator is about 1.5 times its polar radius. And weirdly, that's about twice the pseudo-synchronous frequency that you expect from the dissipation of linear tides. So it's quite surprising that a system would be rotating basically much faster than you expect if all this dissipation is going on. And what we think happens, and when I post-process those simulations, it seems like the breaking waves are actually depositing angular momentum into the surface layers, and that basically shock-mediated dissipation is driving the spin up. So if that ends up being true, in seeing nonlinear tidal dissipation in action, maybe a feature of that is this really kind of runaway of the spin rate. Second, a question in nonlinear tidal dissipation for a long time is, where does the dissipation happen? You can imagine if you put the heat down in the middle of a star. In the sun, it takes 10 to the 5 years for heat to diffuse from the center to the surface. That will mediate that escape over a very long time. But if you put it on the surface, it can just radiate away. And so we can address that here by comparing the equivalent width under those emission lines, the luminosity of that atmosphere, to the kind of amazing observation of a decay of the orbital period in this system. So it has a Macho telephone number. That's because it was first observed by the Macho survey. And so we have about 25 years of data on this source. And folks were able to measure the orbital period decay to about 11 seconds per year. It's a 32-day orbital period. And that's corresponds to about 100 solar luminosities in this system. The brightness of the star is 10 to the 5, so it's a small fraction of the stellar brightness, but that almost exactly matches the emission line luminosity. So I think that tells us something about, in this particular system at least, the action of tidal dissipation is putting all that energy at the surface, and we're seeing it radiate away from this atmosphere. Okay. As we go on, I wanted to talk about something smaller. So again, we have an evolving star, but so many of the stars that we know actually have lots of stuff in the separations that they'll grow to. So as stars evolve from their main sequence radii to a little bit larger to a little bit larger, they'll actually eventually swallow most of the exoplanet population that we know. And so it's really interesting to think about what the fate of all of these systems is. And in particular, I think there's two aspects of this story that I want to focus on. One is just when a star swallows a planet, there's a decay of the orbit as it falls through that dense envelope. And we'll talk about that in more detail. And the other thing is, in general, this isn't a gentle process. And so there will be ejecta from the star, those cool and radiate and maybe power transients that we can see. Okay, so let's talk about some of the details. For a planet to end up inside a star, it has to be denser than the stellar envelope that it's falling into. Otherwise, basically, it's shredded by tides outside the star and maybe forms a disk around it, something like that. So presumably that happens, but we're talking about planets falling into their stars. And as stars evolve, so I'm imagining here this dashed line is a one solar mass star that starts at 1 solar radius, 10 solar radii, 100 solar radii. What's its mean density? And I'm comparing that to the mean density of the planets in the exoplanet sample. And if we just imagine those planets sitting where they are, not tidally decaying at all, which is not exactly right, then we see that in general, these planets will be swallowed up and plunge into their stars because the evolving stellar envelopes that they interact with are much less dense than the planets themselves. So in the frame of that planet, and I recently got to go to Washington, D.C., and I saw the Apollo capsule that came back down through the atmosphere and how blistered by heat the bottom surface of that is. So think about that as a planet. As this planet is flying through this stellar atmosphere, it's being slammed into by a headwind of stellar material. And sort of relative velocity is close to the Keplerian velocity. And that column of gas that the planet interacts with has a characteristic area that's just the cross-section of the planet. So you can say, what is the momentum flux through that surface? That's the equivalent of a drag force or an energy dissipation rate. That's going to change the orbit of the planet. Just like a satellite that comes into the atmosphere starts to decay and decays faster and faster as it goes into denser layers of Earth's atmosphere, the same thing happens here. So the planet will start at the surface. As it falls a little bit, it interacts with denser material in the stellar envelope and falls even faster. So that heat flux, this power, represents an extra heat source within the star's envelope. And something that we can think about is whether or not that's a big deal. So let's imagine for a moment if we took a grain of sand and threw it at the sun and it fell in. Presumably nothing would happen, right? Because that's a tiny disturbance relative to the sun. And so the key is whether or not this power is big or small compared to the stellar power output already. Because we know, for example, that merging two stars together represents a huge power input and is a gigantic disturbance to the star. So really there must be some trade-off in between these limits. Okay, so let's think about that like a conveyor belt. Here, this is like a sushi conveyor. If you add one piece of sushi to this, it's a small perturbation to the flux of food around this belt. This is the flux of power out from the star. If we add a 1% perturbation to the stellar power, no big deal. But if we add a giant perturbation, if we put an elephant on top of this conveyor belt, that's a big problem for the star. It represents a major perturbation. And so the question is swallowing a planet a big deal or not? Are they in the sort of no problem regime for the star or in a big disturbance regime? So here I'm asking that question with a Jovian companion. These are some isochrones of different age here, and we're looking at, so let's just look at the maybe 10 to the 9 or 10 to the 10 for just a moment, and we're looking at engulfing a Jupiter at that separation, okay? So once the star has evolved to, say, 10 solar radii, we imagine at that moment you would engulf a Jupiter-like planet. How much power does that put into the star? And it's in a ratio to the stellar luminosity. So a couple of things happen. One thing is, as stars get bigger, they get a lot brighter. So the power, if it's going to disturb the star, has to be much more. And the other thing that happens is as stars get more extended and bigger, in addition to getting brighter, they also get much less dense. So the decay rate of a planet through that low-density atmosphere is slower. And it turns out there's a trade-off. If a star close to the main sequence swallows a Jupiter, it's a major disturbance to that star. We would expect to see something. If a star at the tip of the AGB swallows a Jupiter even, it wouldn't even notice. And so if we think about the future of our solar system, it's a little humbling because that means when the sun swallows Earth, it's not even going to matter for the sun. It's going to be like we're just a tiny, perturbation to the sun. I think the good news is that's in about 5 billion years, so we have other problems that are more pressing. And then we can ask, how many orbits does that falling in take? So like the satellite that's sort of plunging into the atmosphere, does it decay over one orbit, 10 orbits, 10,000 orbits? And what you see is close to the turnoff from the main sequence, it takes of order a few orbits for that infall to happen. And so if we were to draw the orbital path as kind of a spiral with a tightening orbit, we would kind of imagine that that's a pretty loosely wound spiral. These things are falling in pretty quickly. Near the tip of the giant branch, it goes around thousands of times as it decays, presumably. So that's a little bit of a qualitatively different story. Here's a simulation from some beautiful work that MacLeod did, where we're seeing a hot Jupiter skimming around the surface of its star, and then we're going to transform and look at this in the plane of the orbit. This is now a slice. And all of a sudden that thing falls in and disappears. And if we look at this, now the upper panel is the star and planet density. The planet's the little one, the star is the big one. And the lower panel is just the stellar material. And what I want you to notice is that the star, the interaction with that ram pressure strips a bunch of material off the planet. So not only is this Jupiter mass planet falling in, it's also getting ablated on the way to the point where it eventually just kind of disappears. And there's a really kind of sharp transition from that skimming phase to that almost radial infall at the end. So one thing that's interesting about that ablation of the planet is that in the process of being kind of eaten, the planet itself is destroyed. It's no longer kind of persistent. That kind of tracks with what we would imagine. Another thing is that that deposits all that planetary material both on the surface and in the envelope of the star. And people have thought really hard about the chemical enrichment signatures that that would imply. So we talked a little bit what happens to the planet as it goes in. Now I want to actually go backwards chronologically and think about what happens in that moment as it plunges in. You might have seen in those simulations a little bit of gas is flung out. And as that little bit of gas is flung out, it powers a mission that we can see. So this is a simulation of a coalescing binary star system with a 1 to 10 mass ratio, whereas like a Jupiter to planet is 1 to 1,000. And what I want you to see here is that as these come together, there's so much material spilling out into the surroundings of this binary. And as the closer they get, the faster that and more mass-rich those ejecta become. They're continually sweeping into each other, and you get these nested layers of spiral shock waves. And that powers a mission that we can see. And so in the context of stellar coalescence transients, we call these luminous red novae. They're luminous because they're flares, and they're red because they don't have an extra heat source. They just cool off over time. And so their color evolution is continuously redward, basically. So we're seeing, a bunch of hydrogen gas cooling off and radiating, and so the characteristic temperature gets redder and redder. This class of objects has a number of amazing sources now, but a really important object was called V1309 Scorpius. So this is a galactic transient. It brightened by about 10 magnitudes. Was actually in the Ogle field beforehand, and when folks looked at those data, they found that it was an eclipsing binary, but an eclipsing binary with a decreasing orbital period. So it started with a 1.4-day orbital period, and it was exponentially trending downward. It went through this 10 magnitude flare, and as it came out the other side, there was no evidence of being a binary anymore. It seemed like a single star. And by association, there's basically a growing class of objects, and you can see how long people like Mansi and Shri have been thinking about this class of objects that are between novae and core collapse supernovae. This is a plot from 2011, and this is still where we are today. But with a much richer and more filled-in landscape. And that spectroscopically and photometrically are really kind of defined by the association with that particular transient. And as this class has grown, some trends have emerged between things like the duration of the outburst and the characteristic luminosity. And we can understand those very roughly in terms of the light curve being powered by this expanding material, which is recombining as it expands. And recombination is regulating the characteristic temperature of the photosphere. And so these are contours of the mass and velocity that you would infer from that luminosity duration plane. So we see there are very kind of high mass, fast outbursts, and there are comparatively lower mass, slower outbursts. And in addition, this is a new object that I'm really excited to get to share, ZTF Subluminous Red Novae 2020. And this is some amazing work that I've been doing with Kishali Day, and who discovered this source, and it's seen in ZTF, as I'll tell you, it has properties that are really similar to much of the other objects in this class, but it's down orders of magnitude from the other sources, and in particular, to the best of our knowledge, it shares a progenitor with V1309 Scorpius, and approximate properties, mass, radius. But it's 3 to 4 magnitudes, orders of magnitude fainter. And so to the extent to which these low mass ejections kind of track the mass of the companion that fell in, we think these subluminous events, actually, this whole phase space might be occupied by eating substellar companions. And in this case, I'm going to try to convince you that it's something like a Jupiter mass companion. So here's the ZTF light curve. You see an outburst that fades away over the next couple hundred days. What I think makes this particularly stunning is here's the Y's colors. There's an infrared first precursor, and then really extended luminous phase. And so while there's this relatively brief optical outburst, there's a long infrared lead-in and a long infrared tail. So where could that come from? One thing that we see is in this late stage, the SED really transforms. And so we see the formation of at least 10 to the 6 solar mass, 10 to the minus 6 solar masses. This is not a supermassive planet. 10 to the minus 6 solar masses of dust in those ejecta, we think, from this object being engulfed. And the ISM dust along this line of sight is a couple of magnitudes. Here's its photosphere about 180 days later, and it's compared to a couple other sort of similar transients. This is B38. This is a stellar merger. This is an M star, and what you're seeing is there's features of these like molecular lines, magnesium, titanium oxide, and so you have a cool, mostly pretty featureless, but showing these absorption structures, which is really kind of reminiscent of stellar mergers. And then you have a light curve, which is distinct from other stellar mergers in some really interesting ways. And so, in particular, we see that the luminosity rises to peak, which is about 100 times brighter than the quiescent luminosity of this star. And then it just starts slowly fading away. And the temperature stabilizes at about the hydrogen recombination temperature, a few thousand Kelvin. It stays relatively blue compared to other luminous red novae. And the photosphere at first, expands to, a few solar radii, but then is starting to contract back. And so in a sense, what we think is that this is kind of a milder version of two stars merging. You put them together, and instead of brightening by a factor of tens of thousands, it brightens by a factor of 100. Still a lot. But then we're actually seeing it en route to going back to normal. The source stays bluer. That represents that there's less ejecta mass. And then we're starting to watch this photosphere contract. We think that's a cooling off over time. And this should continue as we go forward. We have some constraints on the progenitor, and some constraints is the right word because it's in the galaxy. We don't know how far away it is, and it's behind a lot of dust. And so it's a project, but you get some drug constraints from the reddened photometry with the uncertain reddening, the dust SED fitting. And that tells us that it's a few kiloparsecs away. It's maybe a 1-ish solar mass star, either near the main sequence or sort of close to evolving off. And if you put those pieces together, our best guess is that it's a star that's actually sort of swallowing its planet. That infrared excess comes from the material that's being flung out as the planet skims along, and then the brightening comes as the star swallows the planet. And so this is a really beautiful illustration by Keith Miller and Robert Hurt here, and it's a joy to get to show that. And this work is actually coming out next week in Nature, and this is a paper led by Kishali Day, and with an incredible contribution from a bunch of you here today, and so I highlighted everyone from Caltech here in bold. So to conclude, I think that as stars evolve, they interact with their companions. And we know this because we see stars with close companions at all phases in their lives. And these events, we're learning, leave incredibly rich traces in the transient night sky. So we see things like very extreme tides that let us probe nonlinear tidal dissipation. We see strong infrared outflows that are probing kind of these dust-rich events that we think might be teaching us about common envelope events and the physics of the formation of compact binaries. And we're seeing optical and infrared transients, which in the case of this really scaled down event, we think is telling us about the engulfment of a planet by its host star and really kind of the fate of exoplanetary systems. So thank you so much for your attention, and we'll be delighted to answer any questions you have. Yeah, so this is a really beautiful point, is that if this star is truly spun up that much and it's all mixed up, that probably changes a number of its properties. All I did was, I think what we don't expect is for example, for the nuclear luminosity to change meaningfully over the course of one orbital cycle. So what I did is I took the observed luminosity and I just asked, how is that distributed around the surface? So I was basically taking into account the oscillatory modulation of the luminosity, but just normalizing to the observed value. So what I don't know is how that modified the evolution of that star. You're 100% correct. And I think, that's interesting to ask, especially in these systems which are quite spun up. And for example, something else we don't know, is it just the surface layers that are spun up? My model, I put it in solid body rotation, but This dissipation is kind of from the outside in the case that the outside is the most affected by the tides. And so that probably depends on the degree of transport inward and all of those details. So the short answer is you're right. I didn't treat that. And the long answer is I don't know how that works out either. Yeah, it's like a star that is rotating that fast. It might remix late, for example.
Because in 10 years, a few solar masses get processed, two stars become one or whatever. Okay. Whereas the star formation rate is only 2 solar masses per year. So one thing I found is most astronomers don't seem to understand that stellar merger actually has a major impact on sort of the lives of stars.
Yeah.
I was on attack recently, and the extragalactic types have no understanding. So.
It's really kind of amazing to think about the fact that these are rare events as we count them in the galaxy right now. Rare being like once every decade, once every year. But in a star's life, it's actually very normal, right? Because this happens to almost every star.
So the point I'm making is if you compare the star formation rate, that is, an IMF is now produced of 2 solar masses per year.
Mm-hmm.
Whereas in 10 years, you're altering more than 2 solar masses in 10 years. So it's a more than a 10% effect on the final mass distribution.
That's 100% correct. Yes, so that's particularly true, I think, in massive stars, where, for example, if you want to make a 20 solar mass star, you're almost as likely to make it as from 10 plus 10 as you are from 1 times 20 when you combine the likelihood of having binaries. And the other thing is there is some time delay, which is a little bit complicated. So to some extent, the instantaneous merger rate now might reflect the star formation history towards the peak of the Milky Way's history. But I think the transformation of these objects is truly really significant. Thanks.
So with all these, tests and Kepler data, so you have accurate geometry data. But do we have the census of how many such merging events, like either stars, small planets, or
Other stars.
whatever sizes? I mean, is there a number for that?
Yeah, so this is, people like Viraj are working really hard on this from ZTF and actually constructing kind of volumetric samples of these things, and that's really amazing to see. And on average, this happens in a Milky Way-like galaxy something like once per year. What's interesting in terms of the events that we see is we've seen sources from 1 solar mass stars, we've seen sources from 30 solar mass stars, and that's because the luminosity function is super steep with mass to the extent that it almost cancels out the IMF. So we are actually quite privileged, I think, in that we get to probe these rare luminous events along with the more common, less luminous events.
So you're saying that it's more likely happening in more massive stars?
In terms of the massive star events are much more rare by orders of magnitude, but they're also orders of magnitude brighter. And so we can see them in a larger volume. And so in terms of our detection rate in a survey, we're actually detecting similar fractions across this spectrum of events, which I think is mostly just a fortunate coincidence. But yeah.
Congrats on your upcoming paper.
Thank you.
What can you say about the planet itself?
Ooh, not much. Yeah, so basically all we get to see is the disturbance of the star by the planet. We never saw the planet. And really we're making the inference that this is a planet just by the fact that it looks just like a skeletal merger, but it's scaled down by a factor of 10,000. And so we never saw the planet, we never saw it transiting, we never saw anything. We just see basically the disturbance of the star, and so it's totally an inference that the planet was there. And basically, we can place some constraint on the minimum mass that could have been responsible for this infrared luminosity in the surroundings, and a maximum mass that we think is sort of consistent with the light curve that we see. But that brackets it between like a Neptune and maybe 10 Jupiter masses. And so I think we're talking about saying that at the level of it's probably a planet is the sort of conclusion that we're able to make. Yeah.
There's a famous Wolf-Rayet star, WR140, that became even more famous with this KWST
Image. So cool.
And so is there something distinctive in the dust morphologies? I mean, I assume what you're plotting there is gas, not really dust.
Yes, correct.
Assume dust.
Yes.
Is there something distinctive about the morphology from the merger scenario that would enable us to accidentally run
Yes.
across events, or if they're observed, is the dust morphology directly tied to anything about the model?
That's a really beautiful point. I think that something that happens in the merger scenario is that as they come together, the kind of fountain of ejecta changes as a function of time, and it gets faster. And that means that the late ejecta catch up with the early ejecta, and there's all these internal shocks, and it basically messes up that beautiful spiral pattern, where I think you get that beautiful kind of persisting spiral pattern to many times the size of the binary when things are basically constant as it's going around. So I almost think that distinctive spiral feature tells us that things were about the same for at least as many spirals as we can count, versus if we were to see that nebula as a result of the stellar coalescence, might not be as clean, I don't think. And in particular, some of the remnants of these objects are bipolar. We think that's because there's a torus of material, the fast material run into it, and it gets sort of squirted out towards the poles. So it might not be as clean, would be my first guess. But in terms of how the gas maps to the dust, it's probably the dust traces those densest features which cool off, which of course you know. But
So for the merger in the star and the planet, do you have any hope from looking at the star's chemistry today to show the spectrum?
yeah,
Metal absorption.
yeah.
I mean, is there, I don't know, some velocity enhancement on the star?
It's hard to tell with the data we have right now, but I think there is some hope. The challenge is that this thing just ejected a bunch of material that formed dust, and so right now it's quite faint in the optical compared to its infrared luminosity, and so getting those spectra is challenging because of that extinction. But there may be more hope by looking at things like mid-infrared spectra and modeling those in detail. Yeah.
Do you expect that there should be a mapping between, say, the rates of this events where a planet is engulfed by a star versus, say, the missing planets that have the short orbital periods?
Yeah, so you're referring to the fact that there's a truncation of the planetary separation distribution at a few stellar radii?
Yeah, could it be because maybe...
Yeah, I think the other thing that happens is, like, if you come too close to a star, your tidal decay time becomes much shorter than the age of the universe. And so we don't see things within a few stellar radii, in part because they would either be tidally disrupted or eaten by their planets, so eaten by their stars. And so this is 100% kind of those missing planets. The fact that there aren't planets that's smaller than some separation corresponds to the fact that those are consumed by their stars. So you're 100% correct there. I don't know if I'm completely understanding, but...
Yeah, just wanted to know if the rates kind of from both this scenario are consistent.
Yes, so it's actually, the rates are interesting. So right now we have one detection in about 1 year of survey, And so maybe there's one per year. Theoretically, you expect hot Jupiters, for example, to get eaten by their stars at most about once per decade. So either we were lucky or there's a little bit of tension in the rates there, and I think that's something we need to understand better. Yes?
Have you ever observed an elevation line molecular emission from the mergers or even
From the remnants, yes.
Indeed,
Yes.
You can think about the outflows from those.
Yes, and basically you see outflows, and you can, in some cases, some of these sources in the galaxy are like 20, 25 years old, and so you can spatially resolve it and make position velocity diagrams, and that's how you can learn that they seem to be bipolar, which at first glance is sort of in tension with the fact that a binary throws everything out in the equator. But maybe it has to do with this reshaping. Yeah. So that's work that like Tomek Kaminsky has done a bunch of.
How did you go with this, the potential planet merger? Was anything, did you observe it with ALMA?
I think there's no detection in the with SMA in this particular source. Yeah. So we tried.
Okay, last question.
I'm interested in the rising part of luminous retinovae.
Yeah.
You're showing the observed event, and it's showing very sharp rising there.
Yeah.
And the relation between this rising part and the initialization, what do you think? What makes
Yeah.
sharp rising part shock?
That's such a beautiful point. And basically that really troubled me when I saw these light curves is how do you get, well, this binary system is living there for 1 billion years, say, and it's changing at the stellar evolution rate. That's so slow. How do you ever get a 1-week transient out of that? And at first I thought, oh, they must be kind of like some head-on collision. But there's actually strong evidence against that now because we see a slow precursor rise in all of these sources. And so it turns out what we think is happening is it's just the exponentiation of the mass loss rate. And so it starts slow, this orbital coalescence, and it gets faster and faster and faster. And also the mass being flung out into the surroundings really ramps up. So for example, in the last orbit, as they plunge in, about 90% of the ejecta are flung out. And so I think the reason that this looks so impulsive, even though it comes from something that starts so slow, is just because we're seeing the tail end of that exponential decay. But yeah, that's a really insightful point.
All right, let's thank Morgan again.
Thank you all.